PostGIS Performance tips. Talking about performance because, is there any question in human history as vexed and contentious as performance? Maybe security, but honestly, it's performance. Nothing elicits interest or emotional response or high volume arguments quite so well as assertions about the performance or lack of performance in the software that people work with every day. It's something about mastering tools, maybe. Like if we know the secret handshake to make things go fast, we value that secret above all other things. And correctness is nice, but really, you don't need to be correct as long as you're fast. And I found that the PostGIS users tend to travel a hero's journey, where first they initially adopt PostGIS and find that PostGIS does everything they wanted and more, and it makes their previous tool look sad and pathetic. And the news is nothing but good. But then something changes. Usually the data gets larger, or there's more joins going on as they get better at SQL. And for whatever reason, things are just not as fast as they should be. So people are all either extremely happy with their performance experience or extremely sad. And rarely do they spend a lot of time in between. And so we come to the question that everyone eventually lands on. How do I make PostGIS faster? And to that question, there can be only one answer, and it is not the answer that you want. It is the maddening, unsatisfying, universal answer to all straightforward computing questions. Yeah, it depends. If there was a one-size-fits-all answer, it would already be implemented. And in fact, there are a lot of things making PostGIS go fast under the covers already. It's not a naive implementation. I actually talked about some of those things under the covers at last year's PostGIS Day. So if you go back to last year's PostGIS Day, there's also a performance talk, but it's very much about the things under the covers more than the implementation and user level. So if we were less upstanding purveyors of fine software, we might do what Oracle did in their Oracle 12i release, which was to literally have a feature flag that made things go faster, but tie it to a very expensive version. So at 12i, they introduced a completely rewritten geometry engine, but they restricted it to the Oracle Enterprise server license level only, which meant on normal server hardware of the time, like with per socket licensing, it would cost about $250,000 to make buffer go faster. That new geometry engine is now standard on all their versions, but at the time, I was impressed by the entrepreneurial spirit of the spatial vector acceleration flag. You want fast? We got fast. Just step right up to the till. So is there a PostGIS faster feature flag? There is not. There is, however, the next best thing, really the only thing that will make things go faster without having to look at your query and your data. And that is simply upgrading your version of GIS. So GIS 3.6 came out in 2017 approximately. The release cadence of GIS is about annually. And for geometry processing operations, GIS just keeps on getting faster. If I put the recent releases on this graph, the recent releases wouldn't look very impressive. You can see like over the 4 years between 3.6 and 3.10, quite a lot of performance improvement, like in some cases orders of magnitude. Get towards the present date, everything's sort of squished together. But if we expand that out and then look at the most recent 4 years, you can see that the trend is in fact still continuing. Not 10x faster, not orders of magnitude anymore, but chipping away, 10% here and 10% there. And some of these improvements are tied to making edge cases faster. Like there's a specific Australia example, like it's a big multi-polygon with a large number of polygons and a large number of vertices, and it exercises the library in a very particular way. So actually, even here in GIS land, the question of what will be fast comes back, as all questions do, to it depends. So what does it depend on? So obviously, this is not a comprehensive list, but for spatial data queries, there is no doubt that these tend to be important axes to think about. How many rows are in the table? How complex is the query? How complex are the geometries being worked on? Things that slow down large collections of points, a lot of small simple things, might not slow down queries on small collections of complex polygons, a small number of very large geometries, and vice versa. And finally, query complexity, like just how much are we counting on order of evaluation to get a fast plan? Can the planner figure out the optimal execution? So firstly, data size, which is to say table size, number of rows, and some very basic recommendations. It's common for people, particularly in data science, to prototype on a small subset and then flip over to processing the whole data set once they get the process nailed down. And this works fine if the process scales linearly. It does not work well if the process scales quadratically. And a table join, spatial or non-spatial, if there's no indexes present, a table join will scale quadratically. So, for example, an unindexed join of 200 record tables, example tables, right? That will produce a very tractable 10,000 condition tests to perform that join. The same join on two still very small 10,000 record tables will produce 100 million condition tests. So probably it'll just never complete, even though the input tables are still very, very small as database tables go. So performance principle number one, indexes. Build them, learn them, and love them. And your first stop is to explain analyze, the explain analyze command. So you can tell if the indexes are being used. And incidentally, why explain analyze, not just ordinary explain? Because explain analyze first generates the plan, that's what explain will show you, which is kind of useful, but it can be hard to evaluate if you're just starting out. And then it also runs the query, explain analyze does, and shows how the plan costs differed from the actual costs. Like, this is very important to finding out the hot points in your query. If you have a 30-second runtime, it's very useful to know if 27 seconds are being spent in one specific place. So indexes. Annoyingly, there are kinds of indexes to choose from, several kinds of, just on the spatial side. But if you feel paralyzed by the paradox of choice, just start with the default gist index. This is the one you'll see in the workshops. It's the one that shows up first in the documentation. Under the covers, it's an R tree with a linear pixelate algorithm and some fancy extra logic for balancing and for edge cases. It's a good index for spatial joins. Like a B tree, it will perform best when dealing with queries of high selectivity, where the filter clauses result in relatively few records being returned. And as with all spatial indexes, thinking about how heterogeneous your data is will help avoid performance bottlenecks, which is something we'll talk about in a second. A much more recent addition is block range indexes under the BRIN access method. BRIN stands for block range index. These are very simple indexes, and thus they're very fast to build, and they're very small to hold in memory. But they're very inefficient at resolving tight query filters. BRIN indexes are only useful, and I cannot stress this enough, they are only useful for data that is laid down on the disk with high spatial autocorrelation. And sadly, it's actually quite hard to get data laid out that way. Like a GPS track of a single item, that'll exhibit strong spatial autocorrelation if you lay it down. Each new point comes in, you lay it down, each new point is going to be spatially autocorrelated with the points that come before. But if you have more than one GPS track, and that's like the way most of these systems work, if you have more than one track being ingested, the spatial autocorrelation will get washed away, though you will retain temporal autocorrelation. So BRIN indexes on timestamps are almost always really handy. Getting a useful spatial BRIN index is a much more rare situation. There are some extract and load processes that end up adding spatial autocorrelation as kind of a side effect of the processing. And the developers who added BRIN indexes to PostGIS originally, they tested against OSM extracts, and they found good enough autocorrelation to support the utility of the index. I used BRIN with some effect for a tile generator that would pull a couple 100,000 records out of a big 1 billion record data set. But to get big wins on that data set, I had to pre-sort it. First, I had to artificially add the spatial autocorrelation to the on-disk storage. So it was quite intensive to prepare the data, and then it was relatively fast to query. Finally, there is a spatial index bound into the SPGIST access method. And this is a quad tree. For some of the tests I've run, I've found smaller indexes, faster build times, and faster query compared to GIST. But for other tests I've run, I've not found that effect. So it's not like a guaranteed win. At a minimum, the SPGIST access method in Postgres has received less attention over the years. So I still tend to default to GIST out of a sense of conservatism and safety, even if I don't necessarily have the metrics to support that. So before committing to an SPGIST index, do a little benchmarking on your use case. Make sure it is in fact a gain over standard GIST before you commit to it. So circling back into GIST. So the R tree is a very nice index, particularly compared to something like a grid index or a geohash in terms of transparently handling data of all sizes, all shapes, and all amounts of overlap. It's a very wonderful general purpose spatial index. Like all spatial indexes, though, it ends up building a search tree that simplifies the geometries to their bounding boxes. All spatial indexes do this. This is good for index size, it's good for build speed, it's good for query speed, but it is an abstraction that can leak terribly because geospatial objects are not, as a general rule, actually box-shaped. The box is a very approximate stand-in. And because it's approximate, this has some consequences. So the natural Earth countries are an excellent example of this. So sure, some countries are roughly box-shaped, like the Czech Republic. That's somewhat box-shaped, even though it is actually probably 30% smaller than its containing box. But to take another example, what about a country like Russia? Holy cow! If you build a spatial index using this data, the box representing Russia will cover not just Russia, but also all of Canada, Greenland, and Western Europe. Feel free to insert your Vladimir Putin joke here. The performance implication of overdetermined bounding boxes is pretty bad, for reasons I'll explain in a moment. But first, how about France? France, surprise! France includes not just the European bit, but also the islands of Saint-Pierre and Miquelon in the Gulf of St. Lawrence, French Guiana, just north of Brazil, and some islands down near Madagascar. So the France bounding box for this data, not very selective. Not a great approximation of France. Most of the areas in the France box are not, in fact, within France. So what are the downsides of these overdetermined bounding boxes? To get a feel, imagine that we wanted to find all the points that fell within Canada. So we wrote this simple spatial join. How does a database actually execute the query? So first, it takes the bounding box of the country, and here we'll just look at the Canada box. And using the spatial index on the points, it finds all the points that meet the intersects condition with the box. So right away, you can see the inefficiency. Like our working set, all the points that are inside the box, well, it is much smaller than the whole original input of all points. It's still at least twice as big as the final result we're looking for. There's a lot of points in that box that are not in Canada. So next step, then for each point in the working set, the point is compared with the full Canada geometry, and whether it is inside or outside is calculated. And here, there's another inefficiency. Even when we're checking the containment status of a point, like down near Vancouver Island, lower left, we have to check against the whole geometry, from Baffin Island to Newfoundland. How can we make the index more efficient and the final filter more efficient? How can we work around the complex geometry of Canada with its large extent and its many, many islands? Performance principle number 2. The more your sets consist of objects of similar size, and ideally small similar size, the more leverage you're going to get out of the table level spatial index, this GIST spatial index on the table. These conditions actually all self-reinforce. Smaller, homogeneous objects will tend to have similar good selectivity. And always, always, always examine your explain, analyze to find your hotspots. Never assume you know where the problem is. Get the evidence. Okay, so how can we manipulate this data to fit our desired conditions? How about chopping it up? What if we chopped up the Canada multi-polygon into smaller polygons, each with no more than 256 vertices? What happens then? Well, you get these polygons that are both more box-shaped, thanks to the way the algorithm works, and also much smaller in terms of memory, since they have a limited number of vertices. They also cover less area, and the area they cover is more localized. And you'll note in this example, I actually subdivided inside a subquery. In production situations, it might make more sense to divide in a materialized view, but it's frequently just as good to subdivide on the fly, since you're getting a lot of the win from the added efficiency of the smaller objects. Now, check out the bounding boxes of these new subdivided query filter shapes. They neatly cover the smaller shapes, and they overlap far less ocean. So each shape is way more selective, and the total collection is also more selective. So when we apply these filter bounding boxes using the index, our working set coming out of the index filter is only slightly larger than the final set. There's no more points in the Arctic or the Western Pacific or in Hudson's Bay. We've significantly reduced the amount of work we have to do, and we haven't even finished getting efficiencies yet. There's more we get out of this scheme. So here's a final bit of efficiency. So for example, when the system has to filter the 6 candidate points that fall within the Vancouver Island bounding box, it only has to pull in the geometry for Vancouver Island in order to complete the test and find the 3 contained points. In our previous query, each point that was pre-filtered by the index had to be tested against the entire geometry of Canada with all the extra work that implies. So fewer points returned by the index pass, and then a much smaller shape to test those points against. Okay, so moving on to principle number 3. A lot of data is just way more detailed than is actually required to answer the questions asked of it. So let's see if we can fix that. So in some ways, like I already covered this problem because the trick we used to make the index search more efficient, it also chopped down the size of the working geometries. And it's really worth pointing out just how important that is and why the trick helps. So there is a substantial penalty to accessing large objects in Postgres because large objects do not reside directly in the table that they appear to reside in. Also, the definition of a large object can be quite small, at least in GIS terms. The database has a page size of 8 kilobytes, which under ideal conditions might hold 512 2D coordinates, vertices, but values are considered oversize once they exceed 2 kilobytes. So that implies a maximum size of about 128 vertices for a subdivide that keeps all the objects out of the toast tables. The oversized values get chopped up and moved into a side table. So that way each piece of data is still below the page size. So the database can happily store very large objects in a table, it looks like, and the user is none the wiser about what is going on behind the scenes. Except what is going on behind the scenes is itself quite computationally intensive. Retrieval of a toasted object involves first finding all the parts, then decompressing them, and then appending them together into the final in-memory object. It's transparent to the user, it's clever, but it is not computationally cheap. The toast system, large object handling in general in Postgres, is predicated on the idea that large things are relatively rare. So when you have a table that is all large things, that assumption can cause bad plans, and every retrieval of any object will have a stiff penalty. So for some data, I've measured toast retrieval as bad as 5 to 10 times slower than direct retrieval. So it's a difference between having a table full of small things that fit inside the page size versus a table with fewer rows but large things that have been toasted out to the side storage. It's way more expensive to do those toast retrievals, even though in aggregate you're actually pulling the same amount of data out. So how to make big things smaller. So one way is to subdivide, but you could also just strip out unneeded vertices and leave the shape as one unitary object. This depends on what you're using the shape for. So I took this shape from a user blog post. They implied increasing levels of simplification to their really ugly shape. The first pass hardly changed it shape-wise. It's hard to tell the right from the left. But space-wise, it got 20% smaller. So that's basically money for nothing. You've reduced your storage size and you haven't really changed the shape of your object at all. The next few passes stripped it down way more, but it still retained its basic area. And for the first one, it was still basically the same shape and 80% smaller than the original. The main thing to note here is that this shape seems to be spatially quite big. So depending on the query pattern, it might make sense to subdivide it. On the other hand, if it's spatially small, then leaving it not divided, but simply reducing the number of vertices might be a better approach. One way to create similar but not the same geometries, there's lots of different ways to do it. For polygonal shapes, and this is like the same idea as a bounding box can proxy for a complex shape that the bounding box surrounds. A concave hull of a polygon can proxy for a fairly complex polygon shape with a lot fewer points. So for polygonal shapes being used as query keys, it might make sense to generate a polygon hull that cuts down the number of vertices that have to be tested, yet still gives you a reasonable proxy to the original. So this is a special case of concave hull where the output is guaranteed to contain the input. But you can specify how much concavity you want. So this is great for chopping off inlets, other complex incisions in a shape, and generally can reduce the vertex count quite a lot, particularly if you pair it with something like ST-Simplify. There is a new class of performance complaints that has become much more common recently, and that's complaints about vector tile generation speed. So for web mapping, a really classic performance problem is just pushing way too many vertices into an output tile. Because at the end of the day, no matter if the format is an image tile or a vector tile, that data is going to hit a screen that people are going to be looking at. And that screen is going to have a fixed number of pixels. There's no point in filling up every pixel with multiple pieces of data. So you want to do is strip out those redundant vertices as early as you can in the processing chain. So for like higher zoom levels, maybe it makes sense to pre-process the data so that they have fewer vertices. For changeable data, maybe run that pre-processing step in a cron job every couple hours. Like use simplification, use hulls, also consider using more advanced tricks. The trouble with standard ST-Simplify and Douglas-Poyker simplification is that it tries to preserve pointy things and it rarely drops things. So the tiny islands don't go away and the narrow inlets don't go away. I find that dilate and erode works great for turning high-res data into low-res data. It smooths out the unnecessary detail and it allows you to simplify to really get the best results. So first dilate, then erode, then simplify. You can see how dilating the shapes like smooths away the narrow inlets, fills them up, and then the eroding returns the shapes to their original coverage area, more or less. And then you can finish up with a fine ST-Simplify to strip out the unnecessary collinear vertices that the buffering process might have injected into the shapes. Okay, last performance principle. Like far and away, the biggest source of performance issues is the area where it depends is the most relevant response. Like why? Why is your super complex query slow? Well, it depends. For new users of SQL, it's really common to shy away from the join keyword. But getting comfortable with the join keyword will help you avoid big mistakes. In this case, the user is performing a potentially huge key lookup instead of just doing a simple inner join. There are all kinds of varieties of this mistake, but it almost always comes down to being a little afraid of join. There's lots of ways to hate joins. The classic way to avoid joins is to just dump all the join conditions into the filter and let the planner sort things out. Depending on your filters and join conditions, particularly as the number of tables involved gets to be larger than 2, you can expect to get unexpected answers. So make sure you experiment a bit and validate that your query does what you want. The filter dump frequently works fine, but it's a good practice to start using explicit joins. So you can take advantage of join features like left joins, also more advanced join layouts like lateral or cross joins. Getting familiar with the join syntax is really its own reward. Similarly, the with clause, which you'll find Postgres developers calling a common table expression, or CTE. When people first get their hands on the with clause, there's a temptation to go wild, right, and pack every step of the query into a CTE until you get something like this, like ad reductio situation, where the user has placed what should be a table reference and moved it, should be a table reference in the from clause and moved it into a CTE. Postgres 12 papered over this mistake by allowing the planner to optimize into CTEs. But in the interest of clarity and saying what you mean, please avoid this pattern. And remember, SQL is not an imperative language. And if you break up every step into a CTE, you're making it hard for the planner to figure out the optimum execution path. So in general, you should aim to get as much work as possible out of each piece of SQL. Like I like to use CTEs to break up real geospatial processing, things like big ST union calls or ST cluster calls. but not for breaking up SQL operations like specifying the target list or carrying out a filter. As I mentioned before, and with vector tiles in particular, there's a bit of magical thinking that goes on, and it's hard to avoid because at some level, a vector tile map is going to want to display the full extent of a table, right? I'm looking at the map. I want to see all the data. It implies ripping the whole contents of a table out and stuffing it into a tile. But don't be surprised if that takes a while because you are transcoding a whole table into the vector tile format. Consider putting a cache layer in front of your tile server so you only pay the price rarely, and also consider simplifying your inputs to match the output scale. A tile generating function or view that switches data sources based on zoom level, that's a simple way to accomplish this. This is also where tricks like dilate and erode can come in handy to turn raw, high detail data into processed, low detail data. At the end of the day, though, you will end up presented with a 5-page SQL query. Someone will come to you with a 5-page query, and they'll say, why is this slow? There is no reason a 5-page query cannot run fast. It is not about the volume of SQL. It's about the volume of data. So remember, unindexed joins can cost quadratic time and vastly expand the volume of data to be processed. Explain Analyze is the tool you need. First, it will tell you which parts of the data are taking time and involve a large number of rows. You always want to see the number of rows falling swiftly as you move from stage to stage of the query. Where you see long run times and large row counts, that's a place to pull out a piece of the query and experiment. Sometimes you will find bad estimates where the runtime and the plan time don't match, like at an order of magnitude level. Analyze your tables, particularly after large data updates and changes. There is no magic answer. It all depends. But learning to read the Explain Analyze will make you very powerful. Also, these days, you can plug the Explain Analyze output into ChatGPT and ask it what it thinks. And it will give you, well, maybe not the exactly correct answer, but usually a good pathway to the correct answer. So summing up, running into performance problems, that's always annoying. But there is a silver lining. If you are using PostGIS hard enough to be encountering performance problems, you are probably already something of a PostGIS expert. Your use case is now beyond the basics, and you are pushing the edges of the system, and you are a PostGIS hero. So congratulations and welcome. I have found that no matter how much I know, there is always, always, always more to learn. So
Thanks, Paul. That's a great talk. Always good to hear about how to get better performance in PostGIS. Yeah. Are there? I think have you answered all the questions in the chat? I think
there is still one
There's
open question in the Q&A set. Yes,
right,
which is
about how do you simplify and preserve topology?
And part of the answer is watch the previous talk, which you gave. So ST coverage simplify would be the new best practice, assuming you have a valid coverage to start with, and the most recent versions. If you don't have the most recent versions, really you're back to either using the topology module, which involves a lot of learning. So you got to learn the PostGIS underbar topology module, load your polygons into there, kind of reach under the covers and to get your hands on the edges and simplify them, and then dump it back out as polygons. It's a bit of a crazy workflow and not necessarily easy to do. The other workflow is equally crazy in its own way, but at least just involves standard PostGIS functions, which is to take the polygons and dump all the rings. So now you have a bunch of line strings. Take all those line strings and dump them through an ST union. So now you have a unique set of line strings. Simplify those lines, and then build back the polygons. The trouble is you still might potentially have bad topology if the simplified version of those lines manage to hit each other. You will at least still have shared edges, but it's not a 100% guaranteed output. Whereas the coverage simplify not only simplifies things, retaining all the shared edges, but also avoids having the edges hit each other. So the output is in fact topologically correct as well as nicely shared and attractive. So not a great answer, but get the latest version and use coverage simplify if you can.
Excellent. Are we, Paula, are there any performance improvements you see coming down the pipeline in PostGIS? I know, I mean, one thing we've talked about is maybe a better spatial join strategy, which is
Yeah, that's more of a research project or serious deep science, because our spatial indexes are built on top of GIST. They don't being able to do what we'd like to do, which is to get away from doing nested loop joins, is what we do now, and be able to do a simultaneous walk down both of the index trees. There was some experimental code that was built to do this maybe 6 years ago. One of the folks at PostGIS Pro in Moscow did an example, but it was a little bit hacky because it required you to know what your GIST index key type was. And it wasn't really clear what it would do if it hit a key type it didn't understand. And the GIST indexes don't necessarily know their key types right off the bat. So it was fiddly, although it did have potential. So it's there possibly, but that's not something which is like likely to happen right away.
too bad.
The one I really want to go after is like spatial temporal. I feel like there's more to be done in the world of spatial temporal.
Excellent.
Yeah. Temp tables versus CTEs. Yeah. I don't know, temp tables versus CTEs. The nice thing about a temp table, unlike a CTE, is that you can index it. So if the temporary data set is large enough, and what you're doing against it is large enough, the value of making a temp table and indexing it before you start doing the work will be high, and that will actually beat a CTE. If the quantities of data you're shoveling through the steps are relatively small, then the temp table is not going to have any advantage. Okay, I see that.